Hello, we are team 14679 and we were the UK winners. I am Philip Ochko.
I'm Max Smith.
I'm Carl Willis.
And I'm Jack Goward.
So, in question 1, we were asked to create a mathematical model that would be able to predict the price of 1 megabit per second of internet a given number of years into the future.
For question 2, we needed to model the optimal bandwidth that could sustain a household for the majority of the year.
And for question 3, we had to find the perfect place to put 4G nodes to cover the bandwidth of an entire geographical region.
So, question 1, the cost of connectivity. In the process of creating our model, our group identified 4 key assumptions that were used, namely that monthly increase rate of prices was the same in both the UK and the US. This is because of the relative similarities in technology and markets in both countries, as well as the lack of data. The second assumption was that the average internet package would also have an average price. It was also assumed that upfront costs only occurred when switching broadband providers, and that broadband was measured in the average peak download speed. Our model used many different variables, with key ones being the speed of the internet after 2 years, the average price of an internet package after 2 years, and the price per megabit of internet after 2 years. The first of the 2 key factors to answering the question was determining the yearly increase in the speed of the internet. Using the data provided, we identified the speed increased at an exponential rate, and we used a data analysis tool to find the exponential regression of the internet speed. This led us to the equation ST equals S0 multiplied by e to the jt, with j being the rate of increase of internet speed and t being the number of years into the future, and S0 being the speed of internet at the base year. The second factor was the average price of the internet packages. This was much simpler to determine, as we found that the price of the internet followed the linear pattern. As such, we created the equation pt equals p0 plus dt, with d being the increase rate in price, which we found to be negative in both the UK and the US. However, we also realized that upfront costs should also be included in the price of the internet. This led us to the addition of u over m to the equation. U represents the average upfront cost, and m represents the average number of months before an individual switches a broadband provider. Finally, we combined the 2 equations to obtain the equation that would give us a result in pounds per month per megabit per second of internet for a given year into the future. From the data provided, we input the variable values for the UK into our equation and obtained the result for the next 10 years. We found that the price of a megabit of internet would drop to 4p in the UK. We repeated this process for the US and found that the price would drop to 3p in the same period of time. Finally, we analyzed our model and determined that it carried both strengths and weaknesses. Our model was simple and in closed form, meaning no complex calculations needed to be carried out. It also accounted for additional costs, which are often overlooked, and was also applicable to any country, given there exists the necessary data. However, it also carries some clear drawbacks. It was impossible to predict sudden technological development, for example, the change to Ethernet. It also does not account for differences in internet service providers, as they all have different pricing strategies and offer different internet packages. It was also only accurate for a fairly short period of time into the future, as because of the nature of our model, it predicted a price that would eventually drop to below 0.
Question 2 needed us to build a model that takes as input information about a household and outputs the minimum internet bandwidth needed to sustain the household for 90% of the year and 99% of the year, both during and before the start of the pandemic. We produced 2 models to do this. We tried to work out what were the most important factors and ignore the rest. We assumed most jobs were at an external site before the pandemic and had a work from home arrangement during the pandemic. We assumed people do not use the internet at school, work, or at night, but a more sophisticated model would have used the age of a person to predict a sleep routine. Additionally, we assumed that if 2 different internet using activities occurred at the same time, it was because 2 different people were doing the activities. We don't have data to work out if this is the correct assumption. Assumption 3.2.4 is incorrect, but it turned out to be irrelevant, and we'll return to this in due course. And the question was about an entire year, but we figured that a single week would be a representative sample because it had the correct proportion of work and rest. The Markov chain model divided time into 1-minute segments and would predict what would happen in each time segment based on what was happening in the previous time segment. So a state must fully capture all the factors that will affect the probability of the next state. We made doing each internet using activity be a state. This meant that the only information the model had to predict what someone would do in 1 minute is the activity they were doing right now. We had historical data about how long various activities take on average. We needed to find the probability P of continuing an activity that would force its mean duration to be T. Initially, we made a mistake and came up with the formula on screen. But in reality, the correct expression is 1 over T for ending an activity, or T minus 1 over T for continuing with an activity. And the proof we have since derived is on screen. We assumed different activities were probabilistically independent. This let us add a null state, or in the paper we called it a free time state, which represented activities that don't require the use of the internet. Excuse me. The variables B and D represent the probabilities of moving away from and to the null state. Moving between activities is always via the null state. On screen are some extra variables, which we didn't include explicitly in the paper. As we already said, E could be found just by taking the reciprocal of each entry in D. To compute B, we took how many minutes an activity is done on average in a day and divided it by the number of minutes in a day.
This is not quite the probability of starting an activity, but since all the activities were so short, as you can see on screen, we assumed that the difference would be insignificant. In the top left, the definition of the transition probability matrix for person C is given. It was simple due to the use of a null state. We used matrix exponentiation to find out what the probability of being in a given state will be after some number of time steps. The binary exponentiation algorithm made the computation much faster. To get the total bandwidth in the whole household, we looked at every possible combination of states the members of the household could be in and worked out its probability and the bandwidth it would use, and whether that bandwidth would exceed the bandwidth of the internet package. We summed up the expected downtime in each minute to get the expected downtime over the 7 days of simulation. Assumption 3.2.4 we mentioned earlier is therefore irrelevant because summing random variables is subject to linearity of expectation and doesn't care about independence. The Monte Carlo simulation model was in essence just a computer program which randomly simulated the behavior of a household. We would specify each member of the household as a quadruple in a list, where the quadruple's elements are age, time spent at work or school, and time spent asleep, and days of the week spent away from the household. Our models were backwards. Instead of telling us the optimal bandwidth threshold to get a certain uptime, our models told us the uptime given a certain bandwidth threshold. We could test every single bandwidth to find which one gave us the perfect uptime, but we realized that adding more bandwidth will always increase the internet uptime or keep it the same. So we could use the binary search to repeatedly chop the search space in half very quickly. The results for the Markov chain were very poor, but it seems that the Monte Carlo model used very similar assumptions. So the issue with the Markov chain was probably one of implementation. To summarize, the Monte Carlo model produced better results that clearly demonstrated the effect of the pandemic on schooling and work, but which isn't as mathematically useful because of its dependence on a computer. On the other hand, the Markov chain probably could have worked, but we fed it incorrect probabilities such that in practice, it didn't.
And moving on to question 3, mobilizing mobile. In this question, we had to place down 4G nodes in a fictional area to encompass the whole region and give enough broadband for everyone. So as you can see, there are quite a lot of assumptions for this section, but just to summarize, the first 2 assumptions are there because it was a fictional region. We had to assume those because we have no data on this region, or more data because it doesn't exist. The next 3 assumptions are there because they're about the cell tower nodes. They're talking about the region of area they give off. The optimal plan uses the least nodes, they're all the same price. 4.2.6 and 4.2.7 are necessary assumptions, as we call them. We say that they're needed to be able to, for our model to work. They talk that each household will only have a maximum of 2 devices and only 1 computer. Whilst this may not be correct in the real world, they were necessary. And 4.2.8 is part of the at-home broadband, saying if you don't have any devices, you won't have any at-home broadband. So that is a safe assumption. These are our variables. These were all taken from the Excel spreadsheet provided. As you can see, we try to cut down on them. Given unlimited time, we may have used more variables, but we only use these 5. And this is the flowchart made for model development. So using the variables and source 17, which states that half of people with a mobile phone own only mobile phones and no other device that connects to an internet, you can work out the percentage of the population which only own phones. Now using this, the variables again, namely the proportion of households with only one smartphone and also 4.2.6, we could find that the percentage of population with exactly 2 phones, we have the percentage with exactly 1 phone, exactly 2 phones, and now we can find the one with 1 computer and laptop and 1 computer or laptop and a phone. These are all the possible devices you can have apart from having no devices. So if we do 1 minus the sum of all these probabilities, we can find the percentage of people without any devices at all. Using this, we now have all the possibilities. We can find the total number of devices in this region, and using assumption 4.2.8, which said that if you have no devices, you won't have at-home broadband, you could then find the total number of houses with a device, but doesn't have at-home broadband. So they will need constant access to these 4G nodes. They're very important. We then find the total number of devices that need to use these 4G nodes often. And then the total number of then we work out how much broadband this would take. Using this, we created something called max common bandwidth. This uses from question 2, which talks about the broadband needed for SD video streaming and the probability that you would stream an SD video. And using this, we could find how much broadband that would take one region. And that was the max common bandwidth. It's common, but it's the maximum that you would see in a common bandwidth area. So these are the results that this gave us. The most important ones are the final 6, the max common bandwidth for each subregion. Using these is what allowed us to find which nodes we should use, which nodes would be the best that would encompass the region and use all the bandwidth. And using this data, we found that 2 medium nodes placed, as you can see on screen, would be the best. We placed them in the center of each region to make sure we can encompass the whole thing with the radius the node emits. Now, the overview of this question is that it's quite simple. Again, you saw in the variable slide, we didn't need that many variables, kept it quite simple. This allows us to apply it to any place, real or fictional, given just those 5 data points. And it gives a clear answer. There are clear answers where to put the nodes, which nodes to use. However, the problems arise from our assumptions 4.2.6 and 4.2.7. Assuming that every household will only have 2 devices whilst necessary, in reality would be incorrect. And same assuming that they could only have a maximum of 1 computer or laptop. Also, which creates problems with source 17, which stated that half of the people owning a phone own only phones. Whilst this is correct globally, in a area with higher or lower rates of poverty, this would be different. However, given unlimited time, the Excel spreadsheet provided did give poverty rates, so we could have calculated this more closely, but we just didn't have the time to do that, unfortunately. Thank you very much for listening to our presentation. We hope you enjoyed it. We did have a nice patriotic national anthem we could play for you as the UK winners, but sadly Zoom won't let us share our screen and share our sound, so we'll have to miss that one out, which I'm sure is a huge shame to everyone. But anyway, thanks for watching, and we're happy to take your questions.
Thank you. That would have been awesome. Congrats to our first UK team ever. Okay, thank you. And now we just have a few questions to follow up.
I think I'll go first. That was great. Thank you. So I have a question for you about your model for question 2 and your approach. So I liked that you used a Markov chain model as your first attempt at question 2. But one thing I did notice was that you didn't account for multitasking. So so I have two laptops and my phone with me right now, and I'm doing different things. I'm just wondering, could you adapt your model to account for multitasking?
A very simple way to add multitasking is to add more states. So each person could have a state for every possible combination of tasks they're doing. But this doesn't scale very well. It's not easy to compute, right? It's exponential in the number of tasks that somebody can do simultaneously. On the other hand, it's likely that there are very few tasks that somebody can do at the same time. What we could have done is, what we did for different members of the household was had a separate Markov chain for each one. If maybe we could have had a separate Markov chain for each kind of like each kind of set of tasks that somebody could do, maybe that would have helped.
Okay.
Again, thank you. I have a question about the Monte Carlo simulation that you used. I was wondering if you could provide some more details about how you actually ran the simulation, but in particular, how did you use the results to get the distribution to find the 90 and 99% thresholds?
To get the 90 and 99% thresholds, we used binary search to locate the bandwidth which causes the Monte Carlo simulation to sort of show a result of greater than 90%. So if the result was like 93% for some input, we would, I guess we'd decrease the bandwidth and then see if that got it below 90% or not. The exact algorithm for the Monte Carlo was just, we took into account time when people are asleep and at work, their age, which determined which activities they do and for how long. Once they start an activity, they do that activity for a fixed amount of time. And we just, at every point in time because we simulate like every minute of a 30-day month, and we sum up the bandwidth used to see if it exceeds the threshold, and then we binary search on that threshold. Yeah. So
then for a given minute, then how do you decide or simulate the needs or what's being used?
We use a pseudo random number generator to pick an activity for each person. Then we used data that we had from the source provided by M3 in order to work out how much that activity would take on average. So for example, downloading a large file had a set amount of time that it would last, and also a set amount of bandwidth it would use on average. And we just assumed that the bandwidth used throughout the performance of that activity was constant, and what the average was. And then we just, we summed that up.
Okay, thank you.
I have a question about Q3. So did you take into account the advantages and disadvantages of using low or high band nodes? It looked like maybe you used mostly mid band, and I wondered if you had taken that into consideration, or if you didn't, how you might.
Well, we did take into account, if I flick back to the slide, it was this max common bandwidth again. Obviously, the medium nodes have a medium bandwidth and a medium range. We looked at using one low bandwidth node, which would cover the entire region. However, the bandwidth that provided was less than, as you can see, there's 718 megabits per second. So it would have been overwhelmed. We could have used high bandwidth nodes. However, we would have had to use more than two, meaning it's not the optimal solution. And so we found that two medium nodes was the only way we could use two nodes and have enough bandwidth to cover this max common bandwidth and cover the entire region with the radius that the node emits.
Thank you. Any other follow-on questions?
Oh, hi. This is Cleve Moeller from MathWorks. I wanted to say to Max, we saw your interview, listened to your interview with the BBC, and I liked your answer that you want to be a programmer. I think that's great. I regard myself as a programmer. Keep it up, study mathematics and programming. Good luck.
Thank you very much.
I've got a question. Last night, during the Academy Awards for movies here in the US, I'm not sure if you guys saw that, Xfinity advertised that they will have gigabit Ethernet, 1,000 megabits. Is that realistic? Are they going to have any customers? Does your model go up to speeds that high?
Unfortunately, our model doesn't really account for such drastic increases in internet speed. Our model mostly handles average internet speed, so what the average user would be able to buy. So no, unfortunately, our model would not be able to encompass that.
But you're trying to predict demand. So your model says Xfinity isn't going to get any customers for gigabit Ethernet. Why are they advertising it?
I'd say our model more predicts the average internet speed. This gigabit internet speed will obviously have some demand, but it's mostly going to be large companies and things like that. Or I wouldn't say it was the average user, at least not for now. Once this is the standard for Ethernet or internet, then our model would be able to predict that, since those would be the values input as the base year. However, it would not be able to predict that given the current data that we possess.
I think it's important to remember that our model is using households. I think the point that Philip produced was quite good. It's that gigabit per second Ethernet is for large companies downloading many files. The average household, really the most intensive thing they do is HD video stream, but with more complex compression algorithms, that sort of speed of internet these days in a household, maybe not a business, but in a household, is almost redundant.
Other questions? Did you have one, Dr. Kavanaugh?
I did. I just wanted to hear from the team members about how that challenge day went. I would like to hear what was the most challenging part of the challenge for you.
For me personally, it was going for the 14 hours. It was a very long time to work on the challenge. But obviously it was very enjoyable and we worked very well together and produced, in my opinion, quite a good solution.
I think the fact that we were in lockdown certainly didn't help. We had to do the whole thing like this, just talking on voice. It was quite hard to show people like what we were doing. I would be scribbling stuff down and then I'd have to try and explain it in words, whereas I could just show them the formula perhaps next year. That's a challenge that we just had to overcome. Screen sharing, those sort of things help us with that. And obviously we did a fair bit of practice. So you get used to using the software, you get used to talking about the things in that sort of way. So that helped, but it still wasn't ideal. We still came across that roadblock during our 14 hours.
Well, you did a great job. Thanks.
Anybody else? We probably have time for one last question.
I'll jump in here. I've been looking at the software for the technical computing part. If you had more time, what would you do with your program, with your software you used to show us?
So I think for the Monte Carlo simulation, there was a lot more like factors that we could have considered. So we only considered, for example, time sleeping, time at work, but we made a lot of really unrealistic assumptions. We said that everybody sleeps at the same time. If we had added a random element, a stochastic element to sleep, I think that would have been a good addition.
I'm not so much interested in changing the model as I am in cleaning up the software so that other people can read what you did with the model you did have.
Oh, I see. Well, a major thing was that to represent everybody in a household, we had a list of tuples, and then for all of the different, the question required us to simulate various different households, and I just put them all together in like a comment, so it's not very usable there. I think having a better data structure to represent several different households, and then to be able to label the household information to make it clear what each entry in the tuple means, what all the different properties of a household, that would have probably been better to label that.
All right, I think with that, we are out of time. It is so great to have you here. Among the hundreds of submissions that were received for this year's challenge, yours is among the very top. So, and it's the very top for the UK. The judges here and those who aren't on today but had the chance to look through your work were highly impressed, and we're very proud. And I look forward to seeing you later this afternoon at the awards ceremony. Thank you.
Thank you very much.
Thanks so much. Great presentation.
Thank you.
Thank you.
Thanks, lads. Bye.